Hello and welcome back to Chopstick Maths. In this video, we shall be solving sum number 4 from exercise 4. Solve the differential equation y into bracket x square y plus e raised to x dx minus e raised to x dy is equal to 0. Now, we can rewrite this given differential equation as x square y square plus y into e raised to x dx, and here we can write this with a positive sign outside by writing the negative sign inside the bracket. So this would be plus into bracket minus e raised to x dy is equal to 0. And let us call this as equation 1. Now let us find out if this given differential equation is an exact differential equation or not. So let us compare this given differential equation with m dx plus n dy is equal to 0 and m equals to x square y square plus y into e raised to x and n is equal to minus e raised to x. Now we'll have to first differentiate m partially with respect to y and then differentiate n partially with respect to x, and if del m by del y is equal to del n by del x, then we can call this given differential equation as an exact differential equation. So let us now proceed to differentiate m partially with respect to y. Now m is equal to x square y square plus y into e raised to x. Therefore del m by del y is equal to x square del by del y of y square. Now since we are differentiating partially with respect to y, we will have to treat x as a constant. Therefore x square needs to be treated as a constant and it would be written outside. So this would be x square del by del y of y square plus, now again here we will have to treat e raised to x as a constant and we'll have to write it outside. So this would be plus e raised to x del by del y of y. Now del by del y of y square is equal to 2y. So this would be x square into 2y. And del by del y of y is equal to 1. So this would be plus e raised to x into 1. Therefore, del m by del y is equal to 2x square y plus e raised to x. Now let us differentiate n partially with respect to x. Now n is equal to minus e raised to x, therefore del n by del x is equal to minus del by del x of e raised to x. Now del by del x of e raised to x is equal to e raised to x, therefore del n by del x is equal to minus e raised to x. Now we can see that del m by del y is not equal to del n by del x. So the given differential equation is not an exact differential equation. Now since this given differential equation is not an exact differential equation, we will now have to find a suitable integrating factor such that when we multiply this given differential equation with that integrating factor, this given differential equation will reduce to an exact differential equation and then we'll be easily able to solve it. Now if del n by del x minus del m by del y upon m is a function of y only, say f of y, then the integrating factor is equal to e raised to integral f of y dy. Now del m upon del y is equal to 2x square y plus e raised to x and del n upon del x is equal to minus e raised to x. Therefore del n upon del x minus del m upon del y upon m is equal to minus e raised to x minus into bracket 2x square y plus e raised to x upon m equals to x square y square plus y into e raised to x. This will be equal to minus e raised to x, and now since there is a negative sign outside the bracket, so when we open the bracket, both the terms inside the bracket would change their sign. So this would be minus 2x square y minus e raised to x upon x square y square plus y into e raised to x. Now this would be equal to minus 2x square y and minus e raised to x and minus e raised to x would give minus 2 e raised to x upon. Now in the denominator we can pull out the y common, so the denominator would be y into bracket x square y plus e raised to x. Now again over here in the numerator we can pull out the negative 2 common outside. So this would be negative 2 into bracket x square y plus e raised to x upon y into bracket x square y plus e raised to x. Now this term x square y plus e raised to x will cancel out each other in the numerator and the denominator, and we will be left with minus 2 by y. That is del n by del x minus del m by del y upon m is equal to minus 2 by y. That is, it is only a function of y, say f of y. Therefore, the integrating factor would be e raised to integral f of y dy. Now, let us substitute the value of f of y in the integral, which is minus 2 by y. So, the integrating factor would be e raised to integral minus 2 by y f of y. Now, minus 2 being a constant, we can pull it outside the integral sign. So, the integrating factor would be e raised to minus 2 integral 1 upon y dy. And integral 1 upon y dy is equal to log y to the base e. Therefore, the integrating factor would be equal to e raised to minus 2 log y to the base e. Now, we can simplify this integrating factor by using the property of log, which says that m log a to the base e is equal to log a raised to m to the base e. So, using this property, we can write this integrating factor as e raised to log y raised to minus 2 to the base e. Now, this integrating factor e raised to log y raised to minus 2 to the base e can be further simplified by using another property of logarithm, which is e raised to log f of x to the base e is equal to f of x. Therefore, using this property, we can write e raised to log y raised to minus 2 to the base e as y raised to minus 2. That is equal to 1 upon y square. So, the integrating factor is equal to 1 upon y square. Now, multiplying equation 1 by the integrating factor 1 upon y square, we get 1 upon y square into bracket x square y square plus y into e raised to x dx plus 1 upon y square into bracket minus e raised to x dy is equal to 0. Now, this would be x square y square upon y square plus y into e raised to x upon y square dx plus into bracket minus e raised to x upon y square dy is equal to 0. Now, in this term, the y square gets cancelled out in the numerator and the denominator. So, we are left with x square plus, now in this term, the y gets cancelled out. So, what is left behind is plus e raised to x upon y dx plus, now in this term there is no common factor, so we'll have to write the entire term as it is. So, this would be plus into bracket minus e raised to x upon y square dy is equal to 0. And let us call this as equation 4. Now, equation 4 is obtained by multiplying equation 1 by the integrating factor 1 upon y square. Therefore, equation 4 is an exact differential equation. And the solution to this exact differential equation is integral m dx keeping y constant plus integral n dy and integrating only those terms in n which are free of x is equal to some constant c. Now, n is equal to x square plus e raised to x upon y, and we have to integrate m with respect to x, treating y as a constant. Now, the first term in m is x square, so this would be integral of x square dx. The second term is e raised to x upon y. Now there is a y in the denominator, so we'll have to treat this y as a constant. So we'll have to write 1 upon y outside the integral sign and integrate e raised to x. So this would be plus 1 upon y integral e raised to x dx plus, now here n is minus e raised to x upon y square. Now we have to integrate n with respect to y, but we have to integrate only those terms in n which are free of x. But if you see here, there is only one term in n and it has a minus e raised to x in the numerator. So we'll have to neglect this particular term. So this would be plus integral 0 dy is equal to some constant c. Now integral x square dx is equal to x cube by 3 by using the formula integral x raised to n dx is equal to x raised to n plus 1 upon n plus 1 plus c, and integral of e raised to x dx is equal to e raised to x by using the formula integral of e raised to x dx is equal to e raised to x plus c. So this would be plus e raised to x upon y is equal to c, and this is the solution to the given differential equation. Thank you very much for watching the video, and if you have liked the video, then please do consider subscribing to the channel. Bye for now and see you in the next video.